we are going to discuss a situation where you have two blocks A and B, and block B is on a horizontal ground. The connection between B and the ground is rough, and block A, as seen in the picture, is on top of block B, and the between A and B, again, the contact is rough. So there's friction in both the surfaces touching each other, and between A and B, and between the ground and the block B. So I haven't given any information like what's the mass of block A, mass of block B, and the coefficient of frictions between each surfaces. I'm not going into details. We will put the symbols appropriately if you need them for the discussion. So my basic question is, the block A is being applied with a force F horizontally, and if the system is in equilibrium, comment on the forces acting on each block. So to do this, I kept the question completely open by saying comment on the forces acting on each block, because we can expand it to other scenarios as well later. So anyway, these type of questions, if you want to analyze them properly, you need to be able to understand the forces acting on each object separately, and especially how to mark the friction and why we mark the friction in a certain way. Then go into equilibrium ideas and connect whatever the connection you have between forces. Okay, and you can go further by connecting it to limiting friction equation, F equals mu r, and then we can talk about scenarios where the equilibrium is not there. One block is maybe accelerating on top of the other, both are accelerating. We can expand this idea to any of these scenarios I pointed out. But to do that, like I said earlier, we need to be able to analyze the forces properly. So I'm going to do this on this video. I have drawn a free body diagram. I've started to draw a free body diagram. Okay, I'm going to separate the block A, separate the block B, and the ground. I have kept a little space. So now I'm going to mark the forces acting on each of these blocks. First, I will think about the horizontal forces, because I'm interested in the motion happening horizontally. We are pretty sure that the vertically things are in equilibrium. By applying a force horizontally, I cannot move them vertically. Okay, so let's first talk about the horizontal forces. Now, here we need the idea of friction. If you don't have that properly in your mind, you have to clarify that. So imagine you knew how to mark the friction. So imagine you knew the idea that friction arises when two surfaces are in contact with each other, but they have a relative motion between them, or a tendency for such motion, a relative motion or a tendency. So if we see that's there, then opposing that, friction is generated. So that's the idea you have to have in mind. So with that idea, let's go into the question. So if you look at the block A, since they say it's in equilibrium, now we know none of the objects move. So we are pretty sure block A and B are at rest relative to each other. But block A is having a force F, having an external force F horizontally. So we could say, although block A is not moving relative to block B, it has a tendency for such motion. So it has a tendency to move to the right. So the friction is generated between those A and B, opposing that. So the block B will oppose the motion or the tendency A has to move to the right by applying a friction force. Let's call it F1. Okay, this friction force is by B on A. Now, according to Newton's third law, you should be able to understand, if block B applies a force on block A has to apply an equal and opposite force on block B. So we will have to mark another F1 on B, which is exerted by block A, right? So you could go to Newton's third law and think like that, or you think in terms of block A. As seen from block A, if block A is to move to the right, block A will see block B moving to the left, right? So it's not happening, but block A would say block B has a tendency to move to the left. So block A applies a frictional force opposing that. Either way you could think. Or you mark one of the forces, use the Newton's third law to mark the other force, or you think in terms of each block separately and oppose the action or the tendency that other block has to move to one side. Okay. Now, if you think in terms of the ground now, let's use a different color. Think in terms of the ground. If the block B, if you think about block B, now this F1 force creates a tendency for block B to move to the right. Okay, and we know it is in equilibrium, so it is not moving, but it has that tendency. So the ground doesn't like that. You could say it exerts another friction force. Let's call it F2. And again, the Newton's third law idea. On the ground by the block B, there is a force called F2. What I marked on the block B, this one, is by the ground on the block B. Now, although I say I mark the F1 first, then mark the F2 first, F2 second, it's not happening one after the other. But you could think of it happening at the same time. At the moment you apply the force, these forces are generated. But we start to think about it one after the other, as in a sequence. Okay. Now, horizontal forces are done. If you want, you can mark the vertical forces too. That's an easy one. But I'm not going to think about the actual line of actions. If I think about the weight of the block A, it's going to be there. Weight of block A. Weight of block B, it's going to be there. Vertically downwards from wherever the center of gravity is. I have assumed the center of gravity to be at those places. And then there is the normal reaction between block A and B, which I'll mark as S. And again, Newton's third law, S. Okay. Then here between the block B and the ground, you have another normal reaction. Let's just call it R. This, what I marked here, is from the ground on the block B. I marked on the ground, if I want, by the block B on the ground. They again Newton's third law pairs, so they're equal and opposite. So I have actually tried to mark them properly with the proper lines of action. Let's put the 90 degrees there because they're normal reaction forces. So this is the complete set of forces that acts on each object. Okay. Now let's think about equilibrium. So if I let me get rid of this. Right, if I think about equilibrium of block A, right, so I'll just write equilibrium of block A, right, of block A. So block A has two sets of forces, one horizontal, the other vertical. Obviously the vertical forces should balance, so S has to be equal to WA. Horizontal forces should balance, so F has to be equal to F1. So you don't need any other arguments to do this. It's simply you mark the forces, then write for the equilibrium. So in any direction, the forces should be balanced. But here, all the forces are either horizontal or vertical. I separately consider the vertical equilibrium and horizontal equilibrium because now the vertical forces has nothing to do with the horizontal forces. Horizontal forces has nothing to do with the vertical forces. Like they don't create any components. Similarly, for the equilibrium of block B, if I do. Now, the vertical equilibrium, as you can see, the force R is upward and there is a force S downward and the weight of the block B. Horizontally, if you think about the block B, you have F1 to the right, F2 to the left. So F1 has to be equal to F2. So this is it. So it's not that difficult. Now you don't have to come here and think about the resultant forces generated by friction or any other connections the block A has on block B, and no other connections are needed, right? If you're thinking about the block A, now you can clearly see all the forces acting on block A. You can clearly see all the forces acting on block B. In the question I mentioned this is in equilibrium, so the forces should be balanced. Now we can also talk about how the limiting friction force between each surface connect to whatever the friction force we have right now. So if you think about the block A, I could say, what is the frictional force acting on it? In this case is F1. F1 is always less than or equal to the limiting frictional force between A and B. And the limiting frictional force between A and B can be written as the coefficient of friction between A and B times whatever the normal reaction you have between A and B. In this case it's S. So that's it for the block A. Now if you think about the block B, it's gonna be F2 is the frictional force between the block B and the ground, and that's gonna be always less than or equal to the whatever the limiting friction force or the maximum friction force between block and the ground. And that value block and the ground is equal to coefficient of friction between block and the ground times whatever the normal reaction. In this case it's R. In the next video we will talk about some numerical calculations regarding this kind of scenario, where I will give the force and the coefficient of frictions between the surfaces, and we will try to figure out whether the applied force is enough to actually move at least one of them. So to which value of force would one block move, the other one will not move, and what kind of coefficient of friction could you have for given force so that both will move. So we can talk about things like that. We will do that in a different video. So that's it for this video. I'll see you in the next one.